Right, so let's go back up here. We have, just rewrite these real quick. T transpose N, T, and then I had big T, P transpose big N. Right? Okay, now let's multiply. I'm going to multiply this equation, the top equation, by ds. Okay, so I have ds here, right? And then I'm going to multiply the bottom equation by d big S, right? Okay, and so then it also multiplying on the right-hand side. I didn't really, let me move these so that I have enough room, but I have ds equals ds equals, right? So I just multiplied both sides. The first one by d little s, the second one by big S, right? And then we said that this, t times the little area is df, and this big T times its area is also df by definition, right? I mean, that's how we define big T. Okay? So these two equations should be equal to each other when you multiply by the respective areas, right? So really what we have is sigma transpose N ds is equal to P transpose N ds. Right? Well, what did we defined this, right, as ds vector, right? And we defined this as d big S vector, right? So now we have sigma transpose ds vector is equal to P transpose d big S vector. Okay? Now we have a relationship, Nansen's transformation for d little s. So plug that in. Sigma transpose is equal to, and I'm just going to put J as a scalar, so I'm just going to move it out front, right? So we have J F inverse transpose D big S is equal to P transpose D big S. Vectors. These are vectors. Right? Cancel, cancel. J F transpose is equal to P transpose. Right? And when we define things, I don't like to define them in terms of the transpose. So let's take the transpose of both sides of the equation to solve for P. So we have P is equal to J F inverse sigma. So P then, P is called the nominal stress. P is the nominal stress. Okay. And P transpose is called I'm going to use the symbol sigma 1 pk. And the reason is we're going to call that the first Piola Kirchhoff stress. You just thought there was only one stress. Okay. We'll see how we might use this in just a second. But now in the next lecture, we're going to show that the Cauchy stress is symmetric. We haven't shown that. You know that from elasticity, right? In small strain, it is, okay? But so next time we'll show, we'll derive the actual, show that the Cauchy stress is symmetric. But so I have a symmetric tensor multiplied by something that's not symmetric. The deformation gradient is definitely not symmetric. and its inverse is not symmetric. So I have a symmetric tensor multiplied by something that's not symmetric. What is that going to give me over here? Non-symmetric. So something that's non-symmetric. So both the nominal stress and the first Piola-Kirchhoff stress are non-symmetric. Okay? Now, I should warn you, I've told you up to now, how many of you bought Malvern or have a copy of Malvern? Okay, a few of you. Because I told you Malvern is the most important book in continuum mechanics, and all the notation that we use comes from Malvern. Okay? Except this one time. Okay? This one time, Malvern actually uses the opposite definition here. So in other words, Malvern uses that what we call the nominal stress is the first Piola-Kirchhoff stress. And he doesn't even introduce something called the nominal stress. Okay? But everything we did, but older books from Malvern, I mean, obviously it goes back to Piola and Kirchhoff. They're the ones that showed this relationship, right? But older books that Malvern took from, Truesdell and others, for some reason he didn't, I don't know why, he got somehow lazy with the notation or what, but what we did in class is right. It's, you know, and it all stems from the fact that some people aren't careful when they use the Cauchy momentum equation, I mean the Cauchy stress equation up here, right? When they use this equation, which is really, well, you know, it's T sigma transpose n, right? And we derived that rigorously and showed that it was the transpose. Well, they immediately then say, well, it's Cauchy stress, which is symmetric, right? So the Cauchy stress is symmetric, so then immediately rewrite the equation as this. T equals this, which is true. A symmetric tensor is its transpose, right? This. So again, we'll show it formally next time. But so then, you know, then they get the second equation down there, and if you were to take then that second equation and derive a similar one that we did, calling this P in instead of P transpose n, then you'd get the opposite definitions down here. Okay, but up until now, I haven't proven to you that the Cauchy stress is symmetric. I'll prove it to you next time. I haven't proven it to you yet, so I can't make that substitution yet. Right? So I have to carry on those transpose around to come up with these definitions. Okay?